Hello, sir. This is Meghnad from ECEA, bearing the roll number 23BQ1A0431. Today, in this session, I am going to discuss about the one of the satellite subsystem, Attitude and Orbit Control System, AOCS. In this, I am going to discuss about the following contents: the introduction of AOCS, need for AOCS and disturbing forces acting on a satellite, the functions of a AOCS, stabilization and control devices, followed by orbit control and station keeping strategies, architecture and performance, and the conclusion. Now let's look into the introduction about the AOCS. AOCS stands for Attitude and Orbit Control System. It is vital subsystem that controls the orientation of the satellite and the position of the satellite in space. Now let's see the role of AOCS in satellite operation. The AOCS keeps the antennas pointed towards the Earth and maintains solar panels facing the sun, and also it ensures proper alignment of payload instruments like sensors and transponders of a satellite. Now, importance in communication satellites. The AOCS provides continuous and reliable communication, which prevents signal loss due to misalignment and increases mission efficiency and service quality. Next, next topic is need for AOCS and disturbing forces. Let's look into the need for AOCS. A satellite in orbit is continuously acted upon by disturbing forces that change its orientation and orbital position. If it is not corrected, antennas will not point towards the Earth, communication links may be lost, and satellite may drift away from its assigned position, and hence an attitude and orbit control system is required to maintain correct pointing and orbit. Next, the disturbing forces acting on a satellite. Satellites are affected by many external forces such as gravitational pull of Sun and Moon, Earth's non-uniform gravity field, solar radiation pressure, Earth's magnetic field, and the atmospheric drag. This is observed mainly in low Earth orbit, which is close to the Earth. Here in this picture, we can observe the disturbing forces acting on the satellite, that is, the solar radiation and the gravity pull from the Sun and the Moon, and the reflected solar radiation forces. These are the forces acting on a satellite, which disturbs the orientation and its position. Next, the effects of disturbance. These forces cause wobbling motion and drift from assigned orbit. Also, these forces change its inclination and antenna misalignment too, which leads to the loss of information and disturbs the communication link between the Earth station and the satellite. Necessity of control systems. Without AOCS, satellites become unstable. Communication links may fail, and satellite lifetime is also reduced. Hence, continuous control is required. Next, let's look into the concept of functions of AOCS. There are mainly two functions of AOCS. They are attitude control and the orbit control. Attitude control maintains the correct orientation and ensures proper pointing of antennas and sensors, whereas the orbit control maintains correct orbital position and performs station keeping maneuvers. Next, the stabilization and control devices. We have two main attitude stabilizations. They are spin stabilizer satellites. In this, the entire satellite rotates at high speed, and the rotation provides gyroscopic stability. It is simple and a reliable system, which is having limited pointing accuracy and used in early satellites. In this stabilization system, we have Despon antenna system too. which rotates opposite to the body spin and keeps the antenna fixed towards the earth. As we observe in the figure that the disper antenna is rotating in clockwise direction, whereas the body is rotating in anti-clockwise direction. This opposite direction of spin makes the satellite stabilize and keeps it in its respective orbit. The next type of stabilized satellites are three-axis stabilized satellites. In this, satellite body does not spin. Orientation is controlled independently and it is a high pointing accuracy. And it is also suitable for modern satellites as shown in the figures. Next, the attitude reference axis. Satellite orientation is defined using three mutually perpendicular axes. They are yaw axis, roll axis, pitch axis. These three are mutually perpendicular to each other, whereas the yaw axis is along z direction and roll axis is along x direction, whereas the pitch axis is along the y axis. The yaw axis is directed towards the center of the earth and the roll axis is directed along the velocity vector of the satellite. This pitch axis is perpendicular to both roll and yaw axis. Next, the control devices. We have three control devices. They are momentum wheels, gas jets and thrusters, and the attitude sensors. The momentum wheels are rotating discs driven by motors, produce reaction torque, and used for fine control. Gas jets and thrusters are small rocket engines as they are used for large corrections and also used for wheel unloading. And the third one is attitude sensors. The satellite is having the earth sensors, sun sensors, and star sensors in it, which are used to provide feedback for control loop. The next concept is orbit control. Now let's see the need for orbit control. Satellites drift due to sun and moon gravity, Earth's equatorial bulge, solar radiation pressure, and orbit control restores proper position of the satellite. Now let's see geo orbit maintenance under the orbit control. For true geostationary operation, the following three conditions must be satisfied. That is, orbit must be circular and inclination must be zero and the longitude must be fixed for a satellite. The next concept is orbit insertion into GEO. Orbit insertion is the process of transferring a satellite from transfer orbit into its final circular geostationary orbit at an altitude of approximately 35,786 kilometers above the Earth. The process goes like after launching a satellite is not placed directly into the GEO. Instead, it is first placed in an elliptical transfer orbit. From this orbit, propulsion systems are used to circularize and align the orbit properly into the GEO. Next, the orbit insertion ensures that the satellite lies in the equatorial plane and has zero inclination with a circular orbit and remains fixed over a specific longitude too. Next, types of geo orbit insertion. The first one is high energy apogee kick motor insertion. The principle follows by a powerful rocket motor is fired at the apogee, which is a highest point of the transfer orbit, to quickly convert the elliptical orbit into a circular GEO. The key features of this insertion method is it is a very high thrust is used, single main burn, the satellite is transferred to higher orbit, and burn duration is just for a few minutes, and this is a fast orbit circularization and higher fuel consumption is happened in this method. This figure represents the high energy apogee kick motor insertion of a satellite into the GEO orbit. Next, the low energy AOCS thruster insertion method. Here, the principle is instead of one powerful burn, small AOCS thrusters are used to gradually raise and circularize the orbit using multiple low thrust burns. The key features of this insertion method is it has low thrust and it uses multiple burns to insert the satellite into GEO. And also the here burn duration is not just for minutes, it is for minutes to hours. Here the insertion process is little bit slower and higher fuel efficiency can be observed. Next, station keeping strategies. We have two types of station keeping strategies. They are east-west station keeping and north-south station keeping. Now let's see about east-west station keeping. That is, it corrects longitude drift and uses tangential thrusters, which requires less fuel, and this is performed every 2 to 3 weeks. Next, the second one is north-south station keeping. This station keeping corrects inclination and uses more fuel, performed every 2 to 4 weeks, and it also determines satellite lifetime. Here we can see the thruster operations. The thrusters are fired in pairs and controlled by onboard computer, and here fuel optimization is essential. Next, usage of thruster in modern satellites. Earlier satellites used the same thrusters for both EW and NS maneuvers. Modern satellites use different maneuvers optimized separately for east-west control and north-south control. This improves efficiency and extends satellite operational life. Now let's see the architecture and performance. Typical AOCS architecture. Main components are sensors, which are used for detect the orientation, and control computer, which is used for processes the data, and the actuators to provide correction. Next, TTC and M interface means telemetry tracking command and monitoring interface, which is used to command and for monitoring. Next, the control loop operation. It is followed by first the sensors detect error and the data is sent to the controller. Next, the controller generates command which is given to the actuators to correct the position. Next, feedback confirms correction, and this process is called as control loop. Okay. This is about the concept of AOCS. In summary, let's see what we have discussed in this. In this, I have discussed about the AOCS maintains attitude and orbit, and it compensates for disturbances that are acting on your satellite. It uses sensors, controllers, and actuators, and also it is very essential for satellite success. And also we have seen the importance of AOCS, that is, it ensures continuous service, improves mission life, and enhances reliability and prevents communication failure. Thank you.